Fluid at rest refers to fluid in equilibrium. So when we talk about equilibrium, we are referring to stationary or something which is at rest. Therefore, fluid at rest is simply means fluid in equilibrium. The study of fluid at rest is referred to as fluid statics. And the term fluid is used to describe any substance that can flow. And this term is used for both liquids and gases. Now, under this fluid at rest, we are going to consider some key concepts. And these key concepts are the density, pressure of fluid, then buoyancy in fluid, then surface tension of the fluid. So in this particular video, we are going to consider the density and pressure, then later on we'll look at buoyancy and surface tension. So let's define density. As the density of a substance is defined as the mass per unit volume of the substance. So density is the mass per the unit volume. So mathematically, this is how we express it. Density, which is rho, is equal to the mass over the volume of the substance. Then pressure is defined as the force per unit area. And mathematically, pressure is equal to force, which is measured in Newton, then over the area, which is measured in meters squared. So this is measured in Newton, and this is measured in meters squared. So the units will be Newton meters squared. Newton meters squared. Or sometimes we refer to this as what? Pascal. So 1 Pascal is equal to this. Now we look at the pressure in liquids, how it is referred to. It is referred to as the hydrostatic pressure. Pressure in liquid is referred to as the hydrostatic pressure. And it depends on the following. It depends on the density of the liquid, then the height of the liquid, and the acceleration due to gravity of the liquid. So we have the density, which is rho. Then we have the height, which is h. Then we have the gravity due to acceleration, which is g. Yeah. So pressure is equal to density times height times gravity due to acceleration. We'll look at how to use this in a past question. So this is our first part. This is our past question. We are talking about the pressure in a liquid is the same at all points in the liquid. That is option A. Option B, decreases with depth. Option C is the same in all directions at a given point. Option D is equal to the atmospheric pressure. So which is the correct answer? So to explain this, you remember that pressure is equal to density times gravity due to acceleration times the height. So we know that the density is a constant and the gravity due to acceleration is also constant. So in effect, the pressure is depending directly on the height, which is the only variable there. Then so this is telling us that since the pressure is depending directly on the height. For equal height at a given point in a particular fluid, the fluid will exert equal pressure for a given height. Therefore, the correct answer will be pressure in a liquid is the same, because it is exerting equal pressure, is the same in all directions at a given point. Therefore, the correct answer is option C. Now let's look at another example. The property of a fluid that is used to determine its suitability as a lubricant is its. Now, you recall that viscosity of a fluid plays a vital role in 1. The flow of the fluids in pipes, then the flow of blood, then also the lubrication of engine parts. Therefore, the property of a fluid that is used to determine its suitability as a lubricant is its viscosity. Then we have another question here from Waec 2013. Which of the following statements about pressure in a liquid is correct? A. The pressure in a liquid increases with depth. B. The higher the density of a liquid, the lower the pressure it exerts. Then C. Pressure in liquid acts only in a direction perpendicular to the size of the containing vessel. Then D. Pressure is independent of the acceleration due to gravity. So what do you think is the correct answer? So let's see. Let's look at this simple experiment. We have a vessel that is filled with a fluid. So when we fit side tubes to this vessel, you realize that the speed with which the water or the fluid comes out or spills out will be greatest at the lowest point over here. So that tells us that the pressure at any point in the liquid increases with depth. Therefore, the correct answer will be option A. Now let's look at this example 2. The diagram illustrates a simple barometer which distance measures the atmospheric pressure. We know the height of the liquid column. The height of the liquid column in a simple barometer will give us the atmospheric pressure. So this will be RQ. RQ is the height of the liquid column in the simple barometer. So that will give us the atmospheric pressure. Therefore, the correct answer is QR. So we have a metal rod of density 7,000 kg per meter cube and cross-sectional area of 0.00127 meters squared, and it has a mass of 1.76 kg. Calculate its length. So we recall the formula for the density of a substance, and that formula is density, which is represented by rho. Density, which is represented by rho, is equal to the mass per unit volume, mass over the volume of the substance. Now recall that the volume of a substance is the cross-sectional area of the substance times the length. So we are interested in finding the length, and we know the volume is cross-sectional area times the length. So we can solve for the length. We can make the length a subject when we multiply both sides by the L, and that will give us length times the row. Length times row is equal to mass over area. But we are not looking for the length times the row, that is length times density. So we divide both sides by the density to get L, which is the length, to be equal to M over area times the density. So we can now fix in the given values. We have the density, which is 7,000. The density is 7,000. Then we have the cross-sectional area to be 0.001257. Then we have the mass to be 1.76 kg. So when we substitute the values, we get the length to be equal to, the length is equal to the mass, which is 1.76 kg. 1.76 kg all over the area, which is 0.001257, 0.001257 times the density, which is 7,000 kilograms per meter cube. So this is in meter squared. So meter squared, then times the 7,000 kilogram per meter cube. 7,000 kilogram per meter cube. Now let's simplify. So when we simplify, you know that this is the same as this is the same as 1.76 kg over. So when we multiply this by this, we get 8.799. 8.799. Then this will be, this and this will go off, left with meter per meter. You have the per meter. Then we have the kg and the kg going off. So you let me write the kg here so that we'll cancel in the next step. So now let's divide. When we divide, we get, when we divide 1.76 divided by 8.799, we get 0.02002. So simply put, this will cater for this. Then we have 0.002 0.2000002 over meter cube, that is over per meter. And this, using the laws of indices, if we multiply both the down and the top by meter, we are going to get 0.2 meters. We are going to get 0.2 meters. So what we are actually saying is that if you multiply this one by meters, which is the same as meter to the exponent of 1 times meter to the exponent of 1, which we have not done anything to this because we just multiply by 1. So this will cater for this because it becomes m exponent 0 and we have m exponent 1. So this will give us the unit to be 0.2 meters. Therefore, the correct answer is A.